Okay, so this is the first question. It says a scientist investigated the radiation. Sorry, I wanted to ask. Did you see the questions I sent to you on WhatsApp?
No.
The math questions, the simultaneous equations, and the other one I sent. You remember, I said I would send you some questions back, when we did maths, the last class, just so that you could practice some more. Difference of two squares and simultaneous equations. Looks like you've not worked on them. But please just try and see what you can do with them, so that I know that you've really gotten a hang of them, the concept behind them. But I think those were among the ones that you said you didn't really have experience with. Okay. So I'll be expecting it, maybe, I don't know, it's stuff you can work on today, maybe later today, and maybe turn in before Thursday, before our class on Thursday. Okay. So let's see. The first question here says, a scientist investigated the radiation emitted by different radioactive isotopes. Okay. Remember, isotopes are different versions of the same element, right? And when you have the same element that has same atomic number, but a different atomic mass. Okay, remember, that's what an isotope is. So it says that the scientists had a sample of polonium. I think that's PO. Okay, the radiation emitted by polonium can be represented by the symbol, okay, helium. Helium, which is He. Okay. It looks like the rotation of your screen is on. So anytime you move your device, it's shaky. Are you moving?
Yes.
For a second.
Okay, Simeon, are you still there? Sorry, no. Okay, can we proceed now?
Yes.
Okay. So it says the radiation emitted by polonium 210 or 210 can be represented by the symbol helium. Okay, that's what He stands for, helium. So it now says which type of radiation can be represented by the symbol helium. Helium is that symbol there is representing helium in terms of its atomic mass and atomic number, okay, which we remember is the atomic number is the number of protons in the nucleus, excuse me, while the atomic mass is the sum of the protons and the neutrons, okay? So it says, which one does it represent? So I'm going to go for alpha. Alpha is the radiation that um, helium represents. Do you have the marking scheme with you there?
Yes.
You don't?
No, no, I do.
Okay, you do. Okay, all right. Okay, so um, so it agrees on that, right?
Yes.
Okay, all right. So let's move on to the second question. It says, how many protons are there in a particle of radiation represented by this? So if you were asked how many protons are there, what would you say?
Two.
There are two. That's because of the two in the He, in that particle there that has the He there, 4, 2. The 2 there is representing the atomic number, which is the same thing as the number of protons. Okay. What does it say next? It says a polonium 210 nucleus changes into a lead nucleus by emitting a helium, or what we have agreed is an alpha particle. This is shown by the following nuclear equation. Okay, so of course I know the next question. What's the value of X? Okay, so what do you think is the value of X?
82.
I didn't hear you. Your voice sounds a bit muffled.
82.
82. Okay, that's correct. Because 82, by the time you add 2 back to it, you would get 84, which is what you have on the left-hand side, correct? Okay, so we can move on now. All right. It says the sample of polonium 210 had an activity of 100 BQ. Not too sure about that unit, but let's see what it says. It says complete the sentence. Choose the answer from the box. After one half-life, the activity of polonium 210 in the sample was, okay, so half-life, half-life, half-life. Half-life is simply the time it takes for half of that sample, for half of the for half of the sample to decay. So this BQ now, I'm not really sure of it, if it's a time thing, but okay, quantum, let's see. I'll go with 50. I'll go with 50, but let's see, what does the marking scheme say?
Yes. 50.
It says 50, right?
Yes.
Okay, okay. Okay, this one says the scientist investigated another radioactive isotope that is a source of gamma radiation. Okay, so what does it say? The count rate is the number of counts detected each second. In 30 seconds, the number of counts detected was 1,500. It says calculate the count rate. Okay, so what do you think about this? It has defined what count rate is for you per second, number of counts per second. And it now goes on to tell you how many counts were detected in 30 seconds. So what do you think will be the count rates?
Um,
1,500 divided by 30, right?
yes.
Okay. So the principle is simple. If you're asking us for what happens each second, then that means the number of seconds will have to be our denominator. Okay. So that's why it's like that, 1,500 divided by 30. And that's going to give us, if the 0 in 30 cancels one of the zeros in 1,500, we'll be left with 150 divided by 3. And that would now leave us with 3 in itself, 1, and 3 in 15, 5. And then the 0 that comes after the 1, after the 15, that's going to give us 50. So the count rate will be 50. 50 counts per second. Are you good with that?
Yes.
Sorry, I didn't hear you. Did you say you're good with that? Did you understand what I did?
Yes.
Okay, okay, all right. Okay, so we can proceed then. Okay. It says he placed a thick sheet of lead between the source of gamma radiation and the detector. What was the effect of the sheet of lead on the count rate? Okay, so um, if you've read some of those texts about radiation, they will tell you that um, in 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 industries where um, machines like X-ray machines and those kind of machines, MRIs, scanners, those kind of machines that emit radiation. For the safety as a precaution, those machines are usually um, placed or have what do you call it? Lead um, casings, I think. So that lead is supposed to protect whoever is operating the machine to minimize um, the accidents of caused by radiation. Okay, so in other words, lead kind of, should I wanted to use the word absorbs, safely absorbs the gamma radiation, which could be harmful. Okay, so if you put a sheet of lead between what's emitting the gamma rays and what's supposed to detect the gamma rays, what do you think will happen?
Um, I don't know.
Remember, the lead absorbs it. So you're putting it between the source of the gamma rays and what's supposed to detect the gamma rays. That's the count rate, what's counting the gamma rays. So what do you think will happen?
Um, still yes, still.
What did you say?
count rate would reduce.
The count rate is going to reduce, definitely. And that's because of the lead. Okay. So that lead is more like a shield. It blocks the gamma rays from getting to the detector, which is the one that's counting the count, that's giving you the count rate. So yes, it's going to reduce. That's the effect. And the reason is simply because lead blocks it or kind of absorbs the gamma rays. Okay. So it can, you just imagine if it's absorbing it, it's definitely going to hinder it from getting to the what do you call it? The machine that's used to measure the count rate, which means that for it to measure the count rate, it has to detect it, right?
Yes.
Okay. All right. So you have any questions on that, or we can move on?
No.
Okay. So it says the lead was irradiated by the gamma radiation. What happened to the lead when it was irradiated by the gamma radiation? Um, the lead atoms became radioactive. The lead gained atoms from the radioactive source. The lead was exposed to gamma radiation. Yes, I'll go with the last one. I'll go with the last one. Does the marking scheme agree on that?
Yes.
Okay. 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 So it says gamma radiation is emitted from the nucleus of an atom. Complete the sentence. Choose the answer from the box. Gamma radiation consists of gamma radiation. I'm trying to remember now. Okay, so I think it's electromagnetic waves. Yes, it's electromagnetic waves. It's not high-speed electrons, no. It's not neutrons, no. It's not positively charged ions, no. It should be electromagnetic waves. Okay, help me confirm from the marking scheme if that's the answer.
Yes. Electromagnetic. Wait.
Is electromagnetic waves correct?
Yes.
Okay, all right. Okay. Figure 2 shows the scientist holding the radioactive source using tongs. Okay. Suggest one reason why using long tongs rather than short tongs was safer for the scientists. Okay, so you want to give a suggestion? You wanna try?
Um. This actually greater distance between the.
Sorry, I didn't get that. It looks like I'm not too now. Maybe there's a sweater or something close to you, the microphone on your device.
You have a greater distance from the radioactive source.
Okay, yes, I can hear you better now. Yes, a greater distance, yes. So that would put him in a safer position, right?
Yes.
Yes. Okay. Okay. So yes, that's a good one. That's a good one. Okay, so we can move on. I think that's enough reason for that question. Okay. Okay. This looks like a machine. But let's see what it says. It says, as the person moves down the zip wire, the block moves upwards. Okay. True. What happens to the gravitational energy of the person as the person accelerates down the zip wire? Okay. Gravitational potential energy. So, in this scenario, and in any scenario really, potential energy usually is it usually increases with height. Okay, so I wanted to imagine for a moment this guy is sliding down the zip wire from the very top where where the pulley is, right? Of course, the weight is going to be somewhere lower, closer to the root of the tree when he's up there, close to the pulley. Then at that point, before he starts sliding down, he's at the highest point he can be as far as that zip wire is concerned. Of course, if we look at it that way. So what it now means is that if potential energy, because the formula for potential energy is mgh, okay, mgh, where m is the mass is the boy's mass or the guy's mass. G is acceleration due to gravity. G, that's usually 9.8 or 10. And then H is the height. So imagine he's at that point close to where the pulley is. That means he's at the highest height he can ever be. Remember, his mass can't change. His acceleration due to gravity is also constant. So guess what? The height is the determining factor now because it can, is when he's closest to that pulley. So before he starts sliding down, that is where he has his highest potential energy. So as he starts sliding down, guess what will happen? His height will be reducing, isn't it? And by height, I mean his height above the ground level. Okay, it will be reducing as he slides down. So just imagine that that's what is happening. So if we check the if we look at the picture now, where he is, his gravitational potential energy is definitely lower than when he was at the beginning of this rope. Is definitely lower. And guess what? It's going to keep on getting lower as he goes down the zip wire. And the reason is simple because of what I explained, that potential energy is given by mass times acceleration due to gravity and then times the height. So anything that will reduce the height will also reduce the potential energy. Okay, I tried to be as simple as I could get, but that's how it came to me. But I don't know if you understood my explanation.
Yes, yeah.
Okay. Okay. So um we can just go with decreases, okay? Okay. It now says what happens to the kinetic energy of the person as the person accelerates down. Okay. So this is the exciting part. Energy can never be uh, can what's that law? Law of conservation of energy. Energy can neither be created nor destroyed. So what that means is that as potential energy is decreasing, kinetic energy is increasing. Okay, nothing is wasted. Maybe one can say, okay, there will be a bit of heat on the wire as as the guy is going down the wire. Yes, true. That's a true fact. But that heat energy is usually negligible. It's not so much. So the kinetic energy will be increasing as the potential energy is reducing. So we're going to go with increase for this one. Nothing stays the same. Okay. Can you okay, can you do that one that you skipped?
Yeah, they give you equation to use to.
Oh, okay. All right, okay. Okay. So it says as the trolley moves, work is done against friction through, and that's what gives you the heat. What does it now say next? What is the effect of this? Some energy is destroyed. Uh, okay. I wouldn't say so. I wouldn't go with some energy is destroyed because that would go against that law of conservation of energy that I stated back then. And it's a law. So laws cannot be broken. What it now means is that I can say that some energy is transferred to the surroundings. Yes. Yes. I'll go with that. Okay. The person oils the wheels on the trolley. Okay. Nice one. I guess he knows there's friction. So what would oil do? Oil is going to definitely reduce the friction and increase his speed. Yeah, that's what I'm going to, that's what's going to happen. So, um, so friction tends to slow people down or slow movement down. So if you reduce friction, then definitely, um, the speed will increase. So are you good with that explanation?
Yeah.
Okay. Okay. All right. A piece of steel is hit. Okay, you skip that one. Okay, that's an experiment. Okay. Okay. Okay, this one has to do with thermal energy. That's heat energy. Okay, so of course, I'm sure you know thermal is another name for heat. Okay. It says the thermal energy when the temperature of the piece of steel is increased by 50 degrees Celsius It says you should calculate it. Okay. Okay. So the mass of steel is 4.0 kg. Specific heat capacity of steel is 420 joules per kilogram per Celsius. And then it says you should use this equation. All right. Change in thermal energy is mass times specific heat capacity times temperature change. Okay, this one is simple. Are you permitted to use a calculator?
Yes, I believe.
Okay. So all you need to do is to multiply 4 by 420 and then multiply by 50. Now take note, the reason why we're multiplying by 50 is because they told us that 50 is the temperature change. Usually temperature changes are measured as differences between the temperature at a lower temperature and the same temperature measured at a higher temperature. Okay. But in this case, they didn't bother to give us the value for lower temperature versus the value for higher temperature, which would have made us to subtract the smaller one from the bigger one. They just gave us the change. So that's why we're using 50 directly. Otherwise, we would have had to say higher temperature minus lower temperature. You got that right?
Yeah, yeah.
Okay. All right. Okay, so 4 times 420 times 50. What did you get?
84,000.
84,000. Okay. So you know the unit, right? The unit for thermal energy is joules.
Oh, yes.
Okay. All right. Okay, so I think we can move on to the next one. Okay. It says the internal energy of the steel increases as the steel is heated, obviously. What is meant by internal energy of the steel? Let's see. Okay, it looks like they want to take us to kinetic theory here. The change in energy of the steel particles as the steel melts. Okay, not exactly. The energy added to the steel particles as they are heated. I think that middle one sounds like the correct thing. But let's look at the third one. The total kinetic energy and potential energy of the steel particles. Okay, that looks like it. I think I would go with total kinetic and potential energy of the steel particles. But that middle one wanted to, I think I would have gone with that middle one if there was no third one. But let's see, what does the marking scheme say?
It says the last one.
It says the last one, right?
Yes.
Okay. Okay. So I think that last one is correct. The one that has to do with the potential and total potential and kinetic energy. Okay, what does this one say? Solid steel cannot be poured. Yes, definitely. It can't be poured because it's still in solid state. So it's only something that's in its liquid form or molten form in terms of a metal that can be poured. I mean, that should make sense. Okay, but what does it say next? It says which statement about the particles in a solid gives the reason why. All right. Okay. Do you want to scroll up a bit? I can't see that last one. The number of particles always stays the same. That's not what tells us why it cannot be poured, because it's still a solid. Number two says the particles are close together. Okay. Is that why? No. I would go with the particles are in fixed positions. Yes, I'll go with that one, the third one. It's not because they have a fixed size. I mean, that one is quite gives itself away as a wrong option. They are in fixed positions. Um, have you heard of the term lattice before? Lattice, Lattice.
Yes.
Okay, good. That's the same, that's the same term that defines how solids are. They're usually in a lattice, okay, held together by strong bonds. So when they're like that, there's no way they can, behave like liquids. It's impossible. The only time they can behave like liquids is when those bonds are either broken down or weakened by heat, more heat added to the solid and at its melting point. Yes, that's when they can become liquid or molten. Okay, so I hope we are good with the marking scheme on that one.
The particles are in fixed position.
Yes, yes. Okay. All right, so we can move on. Okay. Choose the answer from the box. As the piece of solid steel melts, the mass of the steel dash. Hmm. Okay, so what do you think about this one? Does mass increase? Does mass decrease? Or does it just stay the same?
Um, I believe it's the same.
I didn't get that. What did you say?
No, it's the same.
It stays the same, yes. If you remember when I was explaining about potential energy back then in that question, the one of the guy on the zip wire, I said something about mass. I said mass is constant, and that's a good thing. Mass doesn't change, so it's constant, so it stays the same. That's correct. So we may proceed. Are you checking the marking scheme?
Yeah, yeah,
Okay.
this is yeah.
Okay. This one says which diagram shows how the arrangement of particle changes when a solid melts and becomes a liquid. Okay. That first one looks more like it because I can see that when the first one looks like it's in a lattice organized structure, like like you know like a net. You will have organized lines in between rows and columns. Yes. While the one it leads to seems to be, a bit disorganized. It looks like they're now more freer to move and stuff like that. So yes, I think that first one is correct. The first one is correct. Okay. The density of steel decreases as it melts. Okay. So the question now is, okay, no, don't, let me just look at the question. It says, how does the spacing of the particles change as the steel melts? Okay, so let's understand something about steel, about density rather. We've said that density, mass does not change. So any formula, wherever you see mass in, understand that the mass of that substance doesn't change. Other things may be susceptible to change or likely to change, but mass does not change. Now, the formula for density is given by D equals mass over volume or mass per unit volume. Okay, either way, we're still saying the same thing. Mass over volume or mass / volume. What that means is that if mass doesn't change, but we are told here that density does what? Density decreases. Then it's obvious that what is in the denominator on the right-hand side of the equality sign for D equals M over V. Remember, V is in the denominator. Since M does not change, that means that V must increase for D to decrease. Okay? Now, there's a very simple way I usually use to remember that. I want you to consider this, what I'm about to say now mentally. Let's start with 8. 8 divided by 4 equals 2. Okay? Imagine you have a setup like that. 8 over 4, and then you have 2 equals 2 on the left-hand side. 2 equals 8 over 4. Now, imagine that the 8 does not change. 8 cannot change. It's like mass. It's fixed. You now change the 4. Okay, maybe I wanted to, I think I should have switched it. Okay, no problem. You change the 4 to 2. So what that means is we reduced the denominator. What do you think will happen to the answer? 8 divided by 2 will give us what? 4. Did you notice that the answer will increase? In other words, what that tells you is that when the denominator reduces, the one outside will do what? Increase, right? While the vice versa is the case. If the denominator increases, then the one outside, the answer on the left-hand side, will reduce. So that's what is happening here in this density thing, okay? So it means that the volume occupied by those by the particles increases. That's why the density reduces. Remember again, how did I come to that conclusion? Density is equal to mass divided by volume. And based on that simple fact that when you have that kind of setup, whenever you increase the denominator, what is on the left-hand side of the equality sign, which is in this case density, will reduce. I don't know if my explanation was really was that detailed? Were you able to get it?
Yes, yes.
Okay. All right. So you can just say the spacing, the idea of spacing and volume are the same. There's no big deal about it. Spacing, if you have more space, it means that the volume increases. Okay. So what does it say in the marking scheme?
the space between the particles increases and allows the particles to move further apart.
Increases, right?
Yeah,
Mm-hmm. 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 Okay. 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 It allows the particles to move more. Okay. To move. Yeah. Okay. Okay. All right. Let's go on. Is that it for physics?
uh,
No, I was just asking, is that okay? Okay. Okay. I understand. I think okay. Mm. Okay. So here it says choose the answer from the box. Melting is an example of a what? It's a physical change. Do you remember when we talked about chemical changes versus physical changes? Um, an example of a change that can be reversed, right? Something that can be reversed is a physical change. You can think of an example, adding salt to water, okay? You can actually reverse it, right? It's not a permanent change. How do we reverse it? You can simply heat salt water and all the water would evaporate and leave the salt for you, right?
yeah,
Hello, no, are you there?
yeah,
Yeah, I asked the question. Do you remember? You remember when we talked about physical change versus chemical changes?
yeah.
Okay. So a physical change can be reversed while a chemical change can't. Imagine adding salt to water. That's the example I just gave. Um, Salt water, if you heat it, what will happen to all the water?
To evaporate.
Yes, it will vaporize, turn to vapor, and then leave you with the salt. Then examples of chemical changes. I think I still use sodium chloride, table salt. Once Na sodium combines with chlorine, there is no going back. Okay. If you would, I'm not sure that thing is even workable. But if you want to try and separate the sodium from chlorine, it will be under intense heat. As in, the heat is like not something that anybody will be able to stand. Probably done in a furnace or something. So we can take that as a chemical change. So just think about it that a chemical change is a change that cannot be reversed. All right. So so the all the reactions like the chemical reactions that we've seen so far, most of them are irreversible. Okay. So melting is an example of a physical change because it can be reversed. Does the marking scheme agree on that?
Yeah,
Okay. Okay. What does the next one say? It says steel is a mixture of iron and a small amount of carbon. Okay. What does it go on to say? It shows the mass of carbon in 1.0 kilograms of different types of steel. Okay, the one that has low carbon is 2.0, medium carbon 4.5, high carbon 7.0. Okay, it says a 4.0 kg piece of steel contains 18 grams of carbon. Determine which type of steel the 4.0 kilogram piece is made from. You should include a calculation in your answer. Okay, so what do you think we'll do in this case?
Um, find the mass per kg.
I didn't hear you back then.
Find the mass per kg.
The mass per kg, okay. So in this case, they've told us 18 grams of carbon and in 4 kilograms of steel. So which one, what would we do to find that?
Um, the gram divided by the kilogram.
Did you say you would divide?
Yeah.
Okay, all right. I was not too sure I heard you well. So if you divide 18 by 4, what would you get? That's 4.5, right?
Yeah.
Okay, so that means that this sample of steel that we are investigating is the one that is with medium carbon, isn't it?
Yeah.
Okay, all right. So we can just, our calculation is what is going to show that we are agreeing that it's medium carbon. So that's 18 divided by 4.0 is what tells us what it is. Okay. Are you taking a look at the marking scheme?
Yeah.
Okay.
Yes, it is. The one that I did, and then there's also 2.5 times 2.0.
Does it agree? Does it agree with our calculations?
Yes, yes.
Okay. All right. Okay, so let's move on. Okay. It goes on to say the 4.0 kilogram piece of solid steel was heated until it reached its melting point. Okay, of course, steel can melt. What else does it say? The additional energy required to melt the piece of steel was, wow, that's a whole lot. 280,000 joules. It now says, calculate the specific latent heat of fusion of the steel. Use the physics equation sheet. Okay. Specific latent heat of fusion of the steel. Okay. All right. So do you have this so-called equations sheet? Will it be given to you on the exam day?
Yes, it should be.
Okay. But from my own little experience, I know that there's a formula for this guy, specific latent heat, and it's given by Q, that's quantity of heat Q equals mass times LF. That's the LF stands for latent heat of fusion. So it's just a simple formula, M times L, period. Okay. So if I'm to find L, I'll simply divide both sides by M. You stop sharing your screen. Okay, it's back now. Okay. All right. Let me see. So, um, so do you understand what's what's what I said now? Let me see if I can send it. I've not used the chat box today. Let's use the chat box a little. So I said Q equals M times L, latent heat of fusion. So that's going to leave me with L being equals to Q slash M. Okay, so I think Q is 280,000. Sorry, L will be equal to 280,123 divided by 4. And that would, sorry, divided by 4. And that would give me, what did I just do? That would give me that L is equal to 4 in 28 is 7. And then we have a string of 0, 0, 0, 0. That's 4 zeros. 1, 2, 3, 4. Yep. Yep. Okay. That's it. Joules per kilogram. That's the unit. Joules slash kg. Okay. So I hope that agrees with your calculation. Do you want to take a look at what I sent in the chat, or you are good with my explanation?
Um,
Okay. So you understood my calculation, right?
Yes.
Okay. Okay. What's this one talking about? Symbols. Hmm. Okay, before we go to that one, it said Ghana wanted to build an electrical circuit to monitor the temperature in a greenhouse. Okay. Which symbol represents an electrical component with a resistance that decreases as temperature increases? I think it is the last one. The first one is the switch. The second one is what's that thing called? Transistor. That third one looks like it may be correct too, but I'm sure of the fourth one. The fourth one looks familiar. That third one, I'm not too sure of it. But what does the marking scheme go with?
The third one.
The third one?
Yes.
Okay. All right. Okay. I'll confirm what that fourth one is, because that fourth one looks like something I've seen before. Okay. So what does the next question say? When the resistance of an electrical circuit decreases, what happens? The current in the circuit increases, obviously. Current is like a measure of speed of your electrons. So when resistance to all those movements reduces, definitely the current will increase. What does it now say? Choose the answer from the box. Electrical current is a flow of, it's a flow of charge. Let's not get it wrong. It's a flow of charge, electrical charges or electrons, and those electrons are carrying charges. So I'll go with charge, not energy, not potential difference, definitely not power.
Sorry, I was writing.
Okay. Okay, this one is talking about what? It shows the equipment used by the gardener. The resistance meter displays the resistance of the components, okay? Plan a method the gardener could use to find how the resistance of the components varies with temperature. I think this is talking about how the experiment, what the gardener should do during the experiment, right?
Um,
How would we be able to check or verify, or how would he be able to verify that the resistance varies with temperature? Just means that he will need to um, that sensing component will be put in the beaker of iced water, and the resistance will be measured, right?
Yeah.
Are you with me?
Yeah.
Okay. So it will be put in the iced water first. Then I think the next thing would be to be adding small amounts of hot water to the iced water, right? That will help us to be increasing the temperature of the iced water as we go. And then we'll be using the thermometer to check the change in temperature. And all the while, we will be recording what the resistance box. Your screen is no more sharing. Hello, Noah, are you there?
Yeah. That's very important.
Okay. Okay, so did you understand what I explained?
Um, how to do the experiment.
Yes, for the like a method for the experiment to be able to conduct the experiment using the things he has. He has a means to measure resistance. That's the resistance meter. And that resistance meter has a temperature sensing component at its end there. So like I said, what I said first to happen is we'll start with the lowest temperature we can get, which is the iced water, right? By putting it inside the iced water. When after putting it inside the iced water, we will record the gardener will record what the resistance is with iced water. Then after that, we would now start introducing small amounts. Of course, how would we record the temperature? We will remember to use the thermometer. Thermometer is at the end there. The battery is low. Are you going to get your charger or should I proceed? Okay. Okay. So let me continue. Okay. So as I was saying, um, so we'll use the thermometer to record the temperature. Remember, the resistance meter has already given us the resistance. So we record the resistance and use the thermometer to record the temperature. Then there's a kettle there that we can use to heat water, and we'll be adding the heated the hot water rather to the ice water to help us increase the temperature. So as the temperature is increasing, we will be confirming if the resistance is reducing by measuring both the temperature of the iced water and the resistance from the resistance meter. And your screen is off again. Okay. Okay, so did you understand my procedure for the experiment?
Pardon?
Did you understand my explanation for the method, the experimental method that the gardener could use as we suggested?
Yes.
Okay. Okay. If you do, then we can move on. Okay, this one is the graph. Okay, so we're even expecting it to go like this. What does it say? It says the relationship between temperature and resistance of a component is non-linear. I will not say it's linear. Linear would suggest that it's a straight line. So it's non-linear. Um, and we can't take directly proportional. Do you know why?
No.
Directly proportional suggests that as one increases, the other one too increases. But we can see clearly that that's not what this graph is suggesting. Um, as one increases, the other one reduces. But we can establish the fact that it's non-linear. Okay. Um, at the same time, I can't even say it's inversely proportional because inversely proportional suggests that um, as one increases, the other one reduces, but it's at a fixed amount, which would have meant that this graph would have been a straight line graph, but still tilting in the direction it's tilting. So I'll go with non-linear. What does the marking scheme say?
It says yes, when
What does it say?
one, the middle.
Okay, it agrees with non-linear, right?
Yes. Yes.
Okay. The temperature in the greenhouse changed from 10 degrees Celsius to 30 degrees Celsius. Determine the change in resistance of the component between these temperatures. Okay, so I think we will need to go to that graph to make this decision. Can you go? Let's see. Remember, from 10 to 30. From 10 to 30. So we're going to look for where 10 hits the graph. What's the resistance where 10 hits the graph? What value do you see there? That's 200, right?
So 100.
Or 10. What did
So
you get? Okay, I can't really hear you, but if it confirms, if it agrees with what you're saying, let me see. 10 touches the graph at 200 ohms, and 30 touches the graph at what's that? 50, 50, 60. Okay, you're making it larger. Okay, that's fine. 50, 60, 70, 80. Okay, that looks like 80 to me. Okay, so that's 80. So 200 minus 80, that would give me what? That's the resistance change. 200 minus 80 is 120. Yes. Okay. So go back to the question. Let's see what they really want. Is that 120? Yes. Change in resistance is 120 ohms. So we're good to go. Yes, we're correct. It's 120 ohms. Okay. Okay. So are you done? If you're done looking at the what do you call it? Marking scheme, we can proceed. It says 120, right? Okay. Okay. It looks like yours. Okay. Okay. It's back now. It's back now. Okay. Switched again. Okay. I think, okay. Okay. This one looks different. It says the gardener builds a circuit that switches a heater on. Oh, your battery is low. That switches a heater on when the greenhouse gets too cold. Okay. Use the physics equation sheet to answer questions 04.6 and 04.7. Write down the equation that links current, potential difference, and power. Okay. I think that formula is P equals IV, right?
Um,
Okay, you're not too sure.
no,
Okay, so that's the formula. P equals IV. Okay. Okay, then 04.7 says the power of the heater is 2,900 watts. What does it now say? The potential difference across the heater is 230 volts. Calculate the current in the heater. So based on what I just said, let me send you something in the chat. It says P equals I times V. Okay. Yeah, let me space it out. So it looks like a multiplication thingy. So P equals I times V. What's the value for power from the question again? The watts, the number of watts. What's the number of watts?
Oh, 2,900.
2,900. Was it 2,900?
Yes, for the work.
Okay, I'm not too sure myself. Okay, 2,900 actually. And then the potential difference is 230. Okay, so 2,900 equals I times 230 volts. So you're looking for I. So the relationship is multiplication. So for me to find I, I'll simply divide both sides by 230. So that's 2,900 divided by 230. Okay, so can you use your calculator and crunch that? Let's see what we have. Okay, I didn't get that, but let me send it to you in the chat box. I have a calculation there, but you have the value, so yeah. Oh my. So you understood it, right?
Yes, yes, I do.
Okay. Wind power and solar power are both renewable. Okay. They are both renewable energy resources used to generate electricity for the national grid. Which of the following is also a renewable energy? Uh, which of the following is also a renewable energy? Hmm. Um, I think we should go with geothermal. Natural gas, I'm not too sure of natural gas. Geothermal should suggest heat energy in some form. I'm not too sure of it. Okay. Okay. So yeah, what does the marking scheme say?
Geothermal.
Okay. Okay. What does this one say? The The energy transferred by the national grid in 1 second was 36 gigajoules. Which of the following is the same as 36 gigajoules? Giga should be, okay. Let me be sure. Kilo should be 1,000. That's the first one. Times 10 raised to power 3 should be kilo. Okay. So it should be one of these other ones. I'm not too sure now. Maybe we should just go with the marking scheme. What does it say? Which one is the correct one? The last one.
It says that the second to last one, not the third one.
The last one, right? Okay. Okay, this one has to do with calculation of resistance. It says to determine the total resistance of both resistors, a voltmeter must be connected into the circuit too. It says complete figure 9 to show where the voltmeter should be connected. Okay, so I can't annotate on your I can't annotate on your screen, but if we were to put a voltmeter, right, we'll put the voltmeter across the two resistors. We'll put it you see that place where the let me see where the two resistors are. Yes, where the two resistors are. That's we'll put it across the two resistors. Could you help me do a sketch there? Okay, it won't let you sketch, right? I mean, could you sketch on the
No. This paper doesn't allow.
okay, this one doesn't allow. Okay. 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 Let me see. Let me try if this guy can do a whiteboard for me. Uh,
Are you doing something?
Okay, can you see my screen now? Can you see my screen?
Yes, yes, I can see it.
Okay, it's coming up. It says preparing your whiteboard experience. I think this is because it's the first time I'm using it on this phone. I hope it's going to finish up. Okay, just a minute. Okay, can you see my screen now? Okay. Okay, can you see my screen?
Yeah.
Okay. So if a voltmeter were to be connected, this is how to be connected. Is that okay?
Oh, okay, so it'll be well, okay.
Yes, it will be connected across the two voltmeters, across the two resistors, sorry. Okay, just hold on. Let me stop sharing. Okay. Yeah, you can continue sharing now. Okay. The student calculated the total resistance of the two resistors. The student's answer was 26 ohms. Explain why the student's answer cannot be correct. Okay, so It's a very simple explanation, right? Usually, resistors in um in series. What we mean by resistors in series is when they're connected, one followed by the other, right? One followed by the other. That's when they're in series. But when they're in parallel, like what is in that diagram, the total resistance is usually lower than the two resistors combined when they're in parallel. Okay. So there's no way this value can be correct because for it to be 26, imagine um um one of them is 2, the other is going to be 24. So it's not going to be possible. It's not going to be possible that the total resistance will be 26. Um, let me see. Could you scroll up? Let me take a look at the diagram again. Okay. Oh, okay, okay. One is 20, sorry, not 2. 20, and the other one is, and it's saying the total is 26. Okay. Okay. Okay, scroll down, let's see. Then calculated the total resistance of the two resistors. The student's answer was 26. Yes, it can't be correct. It can't be correct because the total resistance of resistors in parallel is usually less than either of them. It's usually less than either of them. So there's no way we can have it that way. Yes. So the idea is this, the formula for total resistance when they are in parallel, right, is given by 1 over R equals 1 over R1 plus 1 over R2. So that's division by 1 is going to make it somewhat less, by the time you want to invert it backwards. Okay, so it's going to be less. That's how it's going to turn out. Had it been we had the value for the second R, maybe we would have been able to um, establish it, but that's how it plays out. Or maybe should we just use random values? I'm just thinking. Okay, so let's check how does the marking scheme explain it?
Um, total resistance
How does the marking scheme explain it?
because the total resistance the total resistance must be less than 20 because the total resistance of the resistors is less than the resistance of the smallest resistor.
Okay, 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 yes. I think it rhymes. Okay, that's fine. Okay. Okay, it says write down the equation that links current, resistance, and voltage, potential difference, which is another name for the voltage, that's V. Okay, so the formula for that one is V equals I times R. V equals I times R. So that's the formula that links both of them. Okay. Then, of course, the next one says when the total resistance of the resistors was 7.5 ohms, the current in the circuit was 480 milliamperes. It now says calculate the potential difference across the two resistors. Okay, the potential difference across the two resistors. Okay, first off, um, the current is not in amperes. Can you see it? It's in milliamperes. So we need to convert it to amperes. And milliamperes means that we have to divide it by 1,000. Okay, to convert it to amperes. Okay, so for me to convert it to amperes, that means what you're seeing there as 480, your screen is not much showing. What you see there as 480 is actually 0.48. Okay. Then let me see, that's for current. Then the resistance, I think, did they say 15? I'm not too sure. Okay, the resistance is 7.5. So 7.5 times 0.48, what do you have? Seven 7.5 times 0.48.
3.6.
3.6. Okay, so that's the answer in voltage. Okay, so please take note. Sometimes the values that we are supposed to use for our calculations, we have to convert them to their standard units before we use them. And this is an example of such. Okay, so always remember to do your conversions. Okay, so are you good?
Yeah.
Okay, all right. Okay, do we have time for one more question?
Oh no, this is a graph.
Oh, okay, that one is a graph, yeah. Okay, the body analysis scales initially show a reading of 0.0. When the student steps onto the scales reading, the reading is 64.8 kilograms. The student steps off the scales and then immediately steps back on. The scales now show a reading of 64.1 kilograms. Okay. The difference between the two values given by the scales is due to a okay, what's the name of this type of error? Okay, so I'm not sure of the name now. It's not, there are different types of error that you can have when taking measurements. There's parallax error, there's another one, I'm not too sure of the name now. Especially when it has to do with something like this that has to do with springs and all that. Okay. So what does the marking scheme say?
It says random.
Random error. Oh, really? I see. Okay. But parallax error is usually that error that happens as a result of, okay, maybe you are not looking, when you want to measure something that has to do with like a ruler, if you're not looking directly above it, you're looking at it from the side, the measurement can be a bit erroneous. So yeah, when you're looking at it from the top versus when you're looking at it from an angle, okay, that's what usually causes parallax error. So yeah, this one I guess is random since, you can't really explain what caused it to change from 64.8 to 64.1. You can't explain it. Yeah. Okay, but it's all good. Okay, so I know you probably had a long day at school today, so I would allow you to rest. But when do you think you can do the math questions and turning for me to take a look?
I think
The ones I sent on WhatsApp.
yes. Yes, I should. Should be able to. I'll have it today or tomorrow.
Okay, today or tomorrow. Okay. Okay, that's fine. That's fine. That's fine with me. All right then. I'll be expecting it. Okay. So enjoy the rest of your day or your evening.
You too.
Yes. All right, bye.